Right, so in the last video we looked at the distribution of sample means, but we didn't talk about what it's going to do for us. That's what we're going to do this time. When we have a population with a mean of whatever and a standard deviation, and we take samples of size n, the distribution of the means of those samples, the distributions of the sample means, are normally distributed, or is normally distributed, with a mean exactly the same as that of the population, and a standard deviation that's the same as the standard deviation of the population divided by the square root of the sample size. Okay, now let's look at how that's going to affect what we're doing here, or what that allows us to do. Let's go with IQs again. We have a population, normally distributed, mean of 10, standard deviation of 15. We've been dealing with it all semester. And I want to know the probability that an individual selected from this population has an IQ of greater than 115. Okay, so we're talking about this tail here. And it should be somewhere in the neighborhood of 32%, I think. But we know how to find that, right? We know to go to our calculator, get our normal CDF, and we're talking about 115 to some ridiculously high number, because we want above. So essentially we're finding between 115 and infinity in a population with a mean of 100 and a standard deviation of 15. And we see that it is about 16% of the population. So we have about a 16% chance that if we grab a person at random, their IQ is above 115. Now, what if we grab a random sample of 4 people out of this same population? Now we're talking not about this population here. This is a population of individuals. If we're talking about a sample of 4 people and we want to know the probability that the average for that sample is above 115, we're talking about the distribution of sample means of size 4. So that's going to have a mean, right, the same as the population, which is 100, but the standard deviation of this population is going to be the standard deviation of our population here, which was 15, divided by the square root of 4. So divided by 2. So the distribution of sample means is going to have a standard deviation of 7.5. So I'm just going to put 107 there and 115 there, and then 93 and 85. I'm not going to put 5s in there. Okay, so an individual being above 115 means more than one standard deviation away from the mean in the population of individuals. But for a sample of 4 to have an average above 115, because the standard deviation of the distribution of the sample means is smaller, there's a lot of words in there. You may want to rewind that and listen a few times. Because the standard deviation of the distribution of sample means is smaller than that of the population, we're actually talking about 115 being 2 standard deviations above the mean. And we know from experience that that should be about 2.5% of the population, or the probability should be about 2.5. So normal distribution, we're talking about 115 to 1,000 in a population of mean 100 and standard deviation 7.5. And that gives us a 2.27, so a little bit less than 2.5%. So 2.3%. Okay, now think about what that means. If we pick a person at random, it's fairly likely, it's not terribly unlikely, that they're going to have an IQ of above 115, but it would be much more unlikely for a group of people selected at random to have an average IQ that was that high. Now, let's take a larger sample and see what happens there. What if we take a sample of 9? What is the probability that their IQ is above 115? Well, our sample distribution for means of that size is going to be centered at 100, right? The mean's still the same as the population of individuals, but the standard deviation of this distribution is going to be the standard deviation of our population, which is 15, divided by the square root of 9. So divided by 3. So it's going to be 5, 105, 110, and 115. So now we're talking about being 3 standard deviations away from the mean. So it's going to be much less likely that a larger sample will have an average that deviates that much from the norm. And those numbers are easy to do. Right? It's the same thing again. Actually, we can call back that same calculation by doing second enter. And all we have to change here is we don't have a standard deviation of 7.5 anymore. We have a standard deviation of 5. Everything else is the same. And we get 0.0013. So that is 0.1% of the time. So again, an individual, a 16% probability an individual selected at random will have an IQ that's that far above the mean. But if we take a group, the probability that the average for that group, because this is a more condensed, less spread out distribution here, the likelihood that our group will have an average IQ that much higher than the mean is much smaller. And even for a group of just size 9, it's ridiculously small. Okay, that's the idea of the central limit theorem. We have been looking at the probability of an individual being a particular distance from the mean. Now we're looking at the probability of a sample having an average that far away. And for that, we have to use the distribution of sample means. The only thing that really changes is that standard deviation, and that drives our percentages way down. And I think that's enough. I don't think we need to worry about this. So that is it for part 3 of the course. And that is it for me making videos for statistics this year. Yay!